Hi, this is Dr. John Bergduff. In this video, we're going to look at graphing quadratic functions. Now, we've heard the term quadratic before. We've looked at quadratic equations, for example. And the connection is pretty straightforward. A quadratic function, written in what we call general form, is a function defined by an equation of the form f of x equal ax squared plus bx plus c, where a, b, and c are real numbers and the value of a cannot equal 0 because that would make the x squared term disappear. So notice that that's very, very similar to looking at a quadratic equation. We would probably just have a 0 where the f of x is. So it's a function defined by a quadratic expression. Here's a nice example that we're going to spend some time looking at. F of x equal negative 2x squared minus 12x minus 13. And what we're going to do in exploring the graphs of quadratic functions in particular is that we're going to see that if the equation can be transformed into a certain alternative form, we can use what we have already learned about graphing techniques earlier on to draw the graph very, very rapidly. So, as it says here, a quadratic function is easiest to graph if the equation that defines it can be transformed to the following form. And you might recognize as you look at this that you might remember that adding or subtracting a number inside a function, like a squaring function, will cause the graph to shift left or right from the origin. Adding a number on the end will cause it to shift up or down. And a coefficient in front of the function will result in some sort of vertical stretch. So if we could only get an equation like this one we're looking at here into this desired form, the graph would be really easy. Let's try that with this particular example. So let's look at f of x equal negative 2x squared minus 12x minus 13 and rewrite that equation in that form that I was hoping for. And the way we're going to do it is we're going to bring back what is now becoming an old friend, completing the square. And that's because we want to create this squared term that you see right here. Now, this will look pretty much like completing the square has looked before, a little bit different, and we'll point out a few differences as we go along. First of all, we're just going to have a lot easier time of things if instead of writing that f of x, we write y. We know that that means the same thing. Let's write y equal negative 2x squared minus 12x minus 13. And think about some things that we've done with completing the square before. So you might remember when we've completed the square before, it's nice if we can get rid of any constant term that's on one side of the equation. Let's do that. So if I were simply to add 13 to both sides, I'd have y plus 13 over here, and adding a 13 on the right side, negative 13 plus 13 would be 0. Now you might also remember from when we've completed the square before that the coefficient of x squared has to be 1 before all the little tricks and things we do work. So let's also make that happen. We can make that happen if we divide both sides by negative 2. And that will require us to split up these fractions. Y over negative 2 plus 13 over negative 2. Those are not particularly pleasant numbers, by the way. Negative 2x squared divided by negative 2. Negative 12x divided by negative 2. Every term divided by negative 2. Over here on the left, let's express this y over negative 2 as negative 1/2 y. And the second term can be written as negative 13 halves. Don't make that into a mixed number or anything like that. And that's equal on the right. Now here's where we finally see some nice things. The negative 2's divide out. You just have x squared. That's what you wanted. And negative 12 divided by negative 2 is positive 6. So x squared plus 6x. So aside from having that extra y term there, this looks like completing the square has looked before. And in fact, what we're going to do next is exactly what we've done with completing the square before. We look at the coefficient of x, we take half of it, So we think about what is half of 6. Half of 6 would be 3. And then you square that number, and that would give you 9, and you add that to both sides. So let's start on the next slide, and we're going to add 9 on both sides. So we would have negative 1/2 y minus 13 halves. I'm going to look back in a second, just make sure I'm not making any mistakes, plus 9 equals x squared plus 6x plus 9. Let's just check. Yep. Negative 1/2 y minus 13 halves plus 9 equal x squared plus 6x plus 9. Great. Now, if we follow that little rule, the expression in terms of x squared should factor as a perfect square. And having done quite a few of these now, I think you can see that. The right side would factor as x plus 3 quantity squared. On the right side, you might think, common denominator, do I really have to do that? You know what? For the reason I'm going to show you in the next step, you really don't. Let's just leave that exactly the way it is. Now, that's completing the square. We see that that's happened. Let's see how that is relevant to the goal we have. Let me go back a slide. This is what we're looking for again. I'll just kind of re-emphasize it. We want this form. And in that form, f of x is by itself. F of x is the same as y. So to get this to be more in that form, I'm going to need to solve for y. So I need to get the y by itself. And although I could certainly do otherwise, an easy thing to do first would be to multiply both sides by -2 in order to get rid of the fractions on the left side. Now, whatever I do on one side, I also have to do on the other, and I'm going to squeeze that in right there. By the distributive law, multiply the -2 across. -2 times -1/2. -2 times -1/2 is a positive 1y. -2 times -13 halves, the 2's would divide out, and it would be a negative times a negative is a positive. That's a plus 13. You can kind of see why it wasn't necessary to find a common denominator here. We're going to get rid of the fractions anyway. -2 times positive 9 is -18. Be really easy to combine those terms. On the right side, it's tempting to say, oh, I know what I need to do. I need to take x plus 3 and multiply it by itself and then distribute the -2 through. But you don't really want to do that because where you will end up is right back where you started from. If you look at the form we're aiming at, it is okay to have some sort of number in front of an x plus or minus h squared term, or factor rather. So we're actually kind of getting where we want to be. So let's not multiply out the right side. Let's leave it just that as it is. And again, we're trying to solve for y. That's easy enough. Let's combine these two terms here. Y minus 5 equals -2 times x plus 3 squared, and then add 5 to both sides of the equation. Some people show the steps in completing the square in a quadratic function a little differently than I do. You'll see that in another video, and by all means you can choose the approach that works best for you. So that tells me that the equation that I originally started with can be put in this special form that's good for graphing. And we can remember what we've already learned about graphing, and from that, draw a sketch very quickly. So this is the function as we have found it to be. And from what we know already, an expression, or excuse me, a function based on the squaring function is going to be a parabola. The plus 3 that you see right here is going to tell you that the origin of the parabola, usually 0, 0, is going to shift 3 units to the left, and the 5 is going to tell you that it shifts 5 units up. So the plain vanilla squaring function y equal x squared would have its vertex at the origin, but we're going to shift that 3 units left and 5 units up, and that puts it right there. Now you might also remember from when we've graphed the squaring function before that if you think about just a few points, you might remember doing this if you think about just looking at the x values -1, 0, and 1 in this basic y = x squared function. The y values are 1, 0, 1, but the important thing, if you remember from when we talked about graphing techniques before, is this tells me that another point is 1 unit to the left and 1 unit up from the origin, and another point is 1 unit right and 1 unit up from the origin. This -2, though, is telling me that the graph reflects over the x-axis, so instead of a parabola opening up, it will open down, and there's a vertical stretch of 2, a factor of 2, so that would tell me that when I start at my origin, I won't go 1 unit left and 1 unit up, I'll go 1 unit left and 2 units down. Let me stay color coordinated here. 1 left, 2 down, and 1 unit right, 2 units down, and a parabola passing through those points. So fairly simply, I get a graph that looks pretty much like this, a nice parabola, and once the function is in this very special form, the graphing is very simple. Let me throw in some extra terms here that we've sort of thrown around a little bit, but not completely to this degree. We talk about the vertex of the parabola. If the parabola opens down, that's its highest point. If the parabola opens up, that's its lowest point. The vertex of this parabola would be the point right here, and the coordinates of that point are -3, 5. That's my vertex. And you can see that makes sense because the vertex, which for the basic squaring function would be at 0, 0, has shifted 3 units left and 5 units up. So the vertex is easy to identify really by thinking about the graph, or certainly once you have the graph, it's a piece of cake. We've talked about the idea of symmetry. Now, this parabola is not symmetric across the x-axis or the y-axis, but it does have a sense of symmetry if you imagine a vertical line, I'll draw it as a dotted line, passing through the vertex. Notice that the left branch and the right branch of the parabola are symmetric across that line. If you could imagine folding the computer screen along that line, the two halves would match up. We call that an axis of symmetry. And parabolas always have them. I recommend you go ahead and sketch the graph, or at least visualize the graph in your mind first, and then you'll see where that axis of symmetry is. The axis of symmetry is a line, so what we have to write when we're asked for the axis of symmetry is the equation of a line. It's a vertical line, so you might remember from another place that vertical lines always have the form, their equations have the form x equals something, and x equal 1, well, x equal what? Well, look at where the vertical line is, where that axis of symmetry is. It crosses the x-axis at -3. The axis of symmetry, very simply, is x is equal to -3. So once you have the graph, you can answer some side questions like, what are the vertex and what is the axis of symmetry? What is the vertex and what is the axis of symmetry? I'll get my grammar right. Okay, pretty quick way to draw that graph once we have it in the right form. Let's suppose we want to improve on that graph by finding the x and y intercepts. Let's pull some ideas that we've also seen in earlier places and talk about what this would look like. Let's talk about the y-intercept first. Or y-intercepts. Maybe there might be more than one. We'll find out. So you might remember that when a graph crosses the y-axis and hits the y-axis, the x-coordinate of such a point would be 0. So you find the y-intercept of a function or any graph by letting x equal 0. In this case, that would be the same as saying, what is f of 0? And that means just plug in zeros wherever you see the x. Negative 2 times 0 squared, minus 12 times 0, minus 13. Pretty easy calculation. You're going to get negative 13. The y-intercept of this graph is at negative 13. Actually, that's going to go off my off my screen here. The lowest point on my little grid is negative 6. Negative 13 would be more than twice that far down. Let's say it's kind of around here somewhere. Imagining stretching that out. More or less. So this graph is going to get very far down very fast. That's the y-intercept, and it turns out there's only one. What about the x-intercepts? Well, again, building on ideas that we've seen before, if you find the y-intercept by letting x equal 0, you find the x-intercept by letting y equal 0. This is going to take a little bit more work. Y-intercept let x equal 0, x-intercept let y equal 0. Now, I don't have my equation stated in terms of y, but f of x means the same thing as y. So I'm going to set y equal to 0 and look at solving this equation. And as you can imagine, there's got to be some connections between quadratic functions and quadratic equations. Finding these x-intercepts will be a matter of solving a quadratic equation. So we need to bring back in the skills that we learned about solving quadratic equations from an earlier point in the class too. Now, I could look at factoring this and so forth, but what I might suggest that we do first, notice all these negatives as coefficients here. I think we would have a better shot at this if there weren't so many negatives, and it is always perfectly legal to multiply both sides of an equation by the same thing. If that thing that I chose was a negative 1, negative 1 times 0 would be 0, but the negative 1 distributed across the trinomial you see here would simply reverse all the signs. So you'd have 0 equal 2x squared plus 12x plus 13. And somehow that just looks much less intimidating. So I look at that and we think about the techniques we know. We think about trying to factor it, and you might take a second to factor it, maybe, or try to factor it. You may have thought about that while I was jabbering along here. I think what you'll find out pretty quickly, though, is you can't find a way to factor it. So we may have to resort to an old friend. We may have to look at the quadratic formula. Let's get a clean sheet of paper here and rewrite what the equation is that I'm going to solve. 0 equals 2x squared plus 12x plus 13. And remind ourselves of the quadratic formula while we're in the neighborhood. X is equal to negative b plus or minus the principal square root, b squared minus 4ac, all over 2a. And hopefully you remember the little song. My a would be 2. My b would be 12. My c would be 13. Let's plug all that in. We would have as my solutions x is equal to negative 12 plus or minus the square root of 12 squared minus 4 times 2 times 13. That's my a and my c, all divided by 2 times a, 2 times 2. Some pretty big numbers here. We might get our calculator out to help us out a little bit. X is equal to negative 12. Oops, almost forgot the negative. Plus or minus principal square root of 12 squared is 144. And 4 times 2 times 13 is 8 times 13, and that is 104. Oh, that's not going to be too bad. And then 2 times 2 is 4. I recognize that 144 minus 104 would just be 40. And we remember that we can simplify radicals by factoring the radicand into a perfect square, like 4, and something left over, 4 times 10. Let's see if I have a little bit more space. Yeah. So we would have x is equal to negative 12 plus or minus, we have the principal square root of 4, that's 2, times 10, the square root of 10, principal square root of 10, divided by 4. Go back a screen just so we can see that that looks exactly right. I just replaced the principal square root of 4 with a 2. I notice that I have a common factor that I could factor out of both the numerator and the denominator. Also, though, I could view this as two separate fractions. Actually, I think that will be maybe a little better this time, where I could write this as negative 12 over 4 plus or minus 2 times the principal square root of 10 over 4. Because I see that I can simplify the 12 over 4 very nicely. That would be a negative 3. And in the second fraction, the 2 at least divides into the 4 twice, and I would have the principal square root of 10 over 2. Now, since I want to use this for graphing purposes, and oh, do you see my mistake there? I lost my negative sign, negative 3. Since I'm using this, going to be doing this for graphing purposes, it would be kind of nice this time if I could find a numerical approximation to what those numbers are. So I would get my calculator out again, and I would separately calculate what is negative 3 plus the principal square root of 10 over 2, and what is negative 3 minus the principal square root of 10 over 2. And I just get my calculator out and work that out. Rounding off to, let's say, 2 decimal places, which is far more accurate than you can graph anyway. The first solution turns out to be negative 1.42 approximately, and the second one is negative 4.58. Those are my x-intercepts. So if I go back to my graph, I can see that I can make it more accurate by adding in these two x-intercepts. The one, again, was at negative 1.42. It's not quite negative a half. And the other one is negative 4.58, just a little beyond negative 4.5. And that gets me a little bit more structure to my graph, especially if I remember that this branch of the graph has to get all the way down here before it crosses the y-axis, and that gives you just a little bit more precision in the graph. Hope that all makes sense. All right. While we're at it, let's ask a few side questions here. This is a recreation of the graph that we just spent so much effort trying to graph carefully. Once I have the graph, I can ask some side questions. I could ask, for example, what is the domain? Once we have the graph, we know that the domain is the set of all values of x that correspond to points on the graph. Because the graph stretches out to the left and the right, looking along the x-axis, every possible value of x will be used. So the domain is negative infinity to infinity. The range is the set of all values of y, and notice that this graph goes no higher than positive 5, so the range is from negative infinity to 5. There is actually a point at 5, namely the vertex, so we'll include the 5. Domain and range, easy to see from the graph. And then another follow-up question, on which open intervals is the function increasing So remembering again from an earlier place, when we talk about intervals on which a function is increasing, we're asking over which interval on the x-axis, as you pass over that interval from left to right, are the y values going up? So if I imagine reading this graph from left to right and looking at the y values, I'm noticing that they go up until I get to negative 3. So the interval on the x-axis is what we report, the interval on the x-axis over which the graph is increasing. Negative infinity to negative 3, that's when it quits going up. Notice that I say that I am looking for the open intervals, so we don't have to debate whether the endpoint should be included. We'll just put a parenthesis. On which open intervals is the function decreasing? Well, continuing to look along the x-axis, as you pass negative 3 and look to the right, notice that your y values are going down, so we would say that the function is decreasing from negative 3 to infinity, again reporting an open interval. Now, in that one example, we did just about everything you could do in the graphing of a quadratic function. We talked about how to rewrite the equation into a form that the graph would be easier to recognize. That involved completing the square. We talked about improving the graph by looking at the x and y intercepts. We talked about what was meant by vertex and axis of symmetry. And we looked at our function to determine its domain and range and on which intervals the function is increasing and decreasing. That's pretty much everything you can ask. All right, hope that makes sense.